So we were talking about quadratic functions, f of x equal to ax squared plus bx plus c, and we concentrated on the vertex. It's either the lowest point or the highest point on the curve. So that's the important point. And we just derived the formula for the vertex of the parabola. If the coordinates x and y coordinates of the vertex point on the curve is hk, then we can use this formula to find out the vertex parabola where h is equal to negative b over 2a and k will be equal to f of h or f of negative b over 2a. So this is the formula we got last time. So let's just use this formula to find the vertex of parabola, so we don't have to go through all the steps to complete the square to find out the vertex of a parabola, as we did before. So in this example, let's find the vertex of the parabola f of x equal to 2x squared minus 8x plus 3. Previously, when we did this kind of problems, we just complete the square and get the vertex at the end. But since we have the formula now, we can use the formula directly instead of doing all the steps. So we just use the formula h equals negative b over 2a. So b is negative 8 and a is 2. These are coefficients for the terms in the quadratic function. Ax squared plus bx plus c. So a equal to 2, b equal to negative 8, and c equal to 3. So negative b over 2a is just negative of negative 8 over 2 times 2, and there are two negatives, so that makes it positive. And 2 times 2 is 4, so 8 over 4 is 2. So h equals 2. So that's the x coordinate of the vertex. And k is just the f of h. So what is plug in 2 for x and to compute this value of the function. So you got the k equals f of 2 equals 2 times 2 squared minus 8 times 2 plus 3. Okay, 2 squared is 4. So 2 times 4 is 8. And 8 times 2 is 16. So we get 8 minus 16 plus 3. And that's just negative 5. So the vertex of the parabola is at 2, negative 5. Okay, so using the formula. Any questions for this example? No question. Okay.
Wait, I have a question.
Yes.
Is h supposed to be a negative 2?
No, a is the coefficient for the quadratic term, so that would be 2.
But isn't it negative 8 over 4?
You got another yeah, you got two negatives. All right. Any other questions? Okay, so a related problem is the maximum or minimum of a quadratic function that actually occurs at the vertex. So when you find the vertex of a parabola, you actually find the maximum minimum of the function. Okay, so they are related, the problem or questions, or the same question actually. Okay, so there are two cases in here. If the leading coefficient a for the quadratic term, ax squared, if a is positive, then the parabola opens up. So at the vertex, you get the minimum. Okay, and if we use the formula for the vertex of the parabola, okay, then x will be negative b over 2a for the h for the vertex, and the minimum value for the function is just f of h or f of negative b over 2a. And on the other hand, if a is negative, a is less than 0, the leading coefficient of the quadratic term, then the parabola opens down, okay? So you get the maximum at the vertex, and you can easily find the maximum of the function um, by using the formula again. So the vertex x equal to negative b over 2a, or h equal to negative b over 2a, and then you just find the maximum value of the function by plugging h equals negative b over 2a for x in the function itself. So that's just f of h, or f of negative b over 2a. Okay. Any questions? Okay, so let's just do an example, find the uh, range of the quadratic function. So this is actually a question asking about the maximum minimum. When you have a question about the range of a quadratic function, it's basically asking you the maximum minimum. For this particular example, f of x equal to negative 2x squared minus 6x minus 1, since the leading coefficient for x squared is negative 2, so that's the negative or less than 0, the parabola opens down, so we got the maximum, right? And the maximum of the function attains at x equal to negative b over 2a. That's the formula for the vertex, remember? So if we plug in b and a into this formula, you get b equals negative 6 and a equals negative 2 in this case. So we got three negatives. That makes a negative for the whole number. Oh, for the whole thing, and then 2 times 2, so that's negative 6. So for we can reduce it to negative 3 over 2 if we cancel 2 both on the top and at the bottom. So that's the h, or x, at the vertex. And then you just plug in that to negative 3 over 2 of h, or x, for x in the function, you get the f of negative 3 over 2. And that will give you the maximum value of the function, okay? We know that the vertex is a maximum. So just plug in that, you get the maximum value of the function. So negative 2 times negative 3 over 2 squared minus 6 times negative 3 over 2 minus 1. Next, negative 3 over 2 squared, you got a 9 over 4. And then negative 6 times negative 3 over 2, you get a 9 if you know, multiply them and simplify it. And 6, you can do it in different ways. You can multiply 6 by 3, you get 18 over 2, you get 9, or you just cancel 2 from 6, you get 3. 3 times 3 is 9, okay? So, and then you get negative 1 at the end, so just add those numbers. Negative 2 times 9 over 4 is negative 9 over 2 if you cancel 2 in the denominator. And then 9 minus 1 is 8, so negative 9 over 2 plus 8, you can add it easily by using the least common denominator 2 and writing 8 as 16 over 2. So you get negative 9 plus 16, which is 7, and you get 2 in the denominator. So the maximum value of the function is 7 over 2. So the range will include all the numbers less than or equal to 7 over 2. If you look at a curve, the function attains all the values less than or equal to 7 over 2, right? So the range of the function is this set y, where y is less than or equal to 7 over 2. Any questions? So this just give you another example of what it means by range of a function. Okay. Next. Find the extreme of the quadratic function. Okay, again, this same kind of question asked in different words. Extreme, it means either maximum. Okay, so the function we have in here is f(x) equals x squared minus 3x plus 1. So the leading coefficient is also is positive. So we're going to get the minimum for the function. And where is the minimum? You just use the formula again. X or h equal to negative b over 2a, and plug in b and a, and we get the negative 3 for b and a equal to 1. So if you do the calculation, 2 negatives makes positive, and 2 times 1 is 2. So we got 3 over 2 for the h at the vertex or x. And then you just plug in 3 over 2 for x to find the actual minimum value for the function. Okay, so we got 3 over 2 squared minus 3 times 3 over 2 plus 1. And 3 over 2 squared is 9 over 4 again. And 3 times 3 over 2 is 9 over 2. Remember how to multiply fractions. Okay, and then plus 1. Again, you can rewrite 9 over 2 as 18 over 4 and 1 as 4 over 4. Not here, but that's what we do. And then you just combine the numerators to get negative 5 at the end, or over 4 as the denominator. So that's the minimum of the function. The minimum of the function is negative 5 over 4. It occurs at x equals 3 over 2, right? So that's the answer for this problem. Any questions? I have no further questions. I'm going to move to the next section. Okay, 2.5. So let me just add the slides in 2.5. Okay. All right. It's we got this thing uploaded, and then I can share it in here. So 2.5 is a long section. We're talking about the properties of graphs. We're going to have different properties of the graphs. So the first topic is the symmetry of graphs. So you can have different symmetry of graphs like we had in the parabola or quadratic functions in the previous section. It has a vertical line axis as the symmetry axis, right? If you draw a line through the vertex of a parabola, then it's symmetric on the left and on the right. So that's a kind of symmetry for the graph. So we're talking about the same kind of things in here. We're going to discuss the graph of equation, not just a function, okay? An equation. It could be a relation, but not a function, okay? Remember, we have relations that are not functions, okay? The graph of equation can be symmetric with respect to x-axis or y-axis or the origin. We're going to discuss those three kinds of symmetries in here. So the graph of an equation is symmetric with respect to the x-axis if the equation is unchanged when y is changed to negative 1. All right. So how do you know a graph is symmetric with respect to the x-axis? So that's just like a mirror uh, on the ground. If you think about the water, that's a mirror on the ground, and we're talking about this kind of symmetries when we talk about the x-axis. So one of the examples is the equation x equal to absolute of y minus 2. So remember, this is not a function, okay? X equal to absolute y minus 2, because you can have two values for each x values. Okay. The positive or negative numbers, you take the absolute value, you get the same number. Okay. So that's not the function. So let's see what kind of symmetry for this equation to have. Well, if you change y to negative y, the equation becomes x equal to absolute value of negative y minus 2. But uh, negative y absolute value is just the absolute y the same. So we got the same equation as the previous one, x equal to absolute y minus 1. So that means the equation is unchanged when you change the y to negative y in the equation. So according to the criterion here, the graph of the equation will have a symmetry across or with respect to the x-axis. So you can see the graph, the upper and the lower part are symmetric with respect to the x-axis, right? So this is the symmetry we are talking about. So that's the first type of symmetry of graph. Obviously, you can talk about the symmetry with respect to vertical axis or y-axis. And in this case, what you do, you just change x to negative x and see whether the equation changes or not. Okay, so the graph of equation is symmetric with respect to the y-axis if the equation is unchanged when x is changed to negative x, as I said. So for example, we want to test the symmetry of the graph of the equation y equal to x squared plus 2. So this time, let's just change the x to negative x and see what happens. Then the equation just becomes y equal to negative x squared plus 2, but negative x squared is just x squared. So we got the equation y equal to x squared plus 2. And that's just the same as the equation we started in the problem. So the equation is unchanged when you change x to negative x. And according to the criterion, the graph of the equation will have a symmetry with respect to the vertical axis. As you see, this parabola, right? It's symmetric with respect to the vertical axis. Left and right half, reflecting to each other, or the reflection of each other, right? Okay, so those are the first two types, and there's another type of symmetry we talk about. That's the symmetry with respect to the origin. Okay, so this is the point symmetry. The previous type twos we talked about are, symmetric with respect to the lines, but this time we talk about the symmetry with respect to point, the origin. So how do you know this? The graph of equation is symmetric with respect to the origin. This time you have to change both x to negative x and y to negative y and see if the equation is changed or not. If it's unchanged, then the graph has a symmetry with respect to the origin. Okay, so for example, let's see the equation xy equal to 4, and we want to find the symmetry of the graph. So if you change x to negative x and y to negative y, and then you get the negative x times negative y equal to 4, but the two negatives multiply to get the positive. So this equation is actually the same as xy equal to 4, which is the original equation in the problem. So that means you change both x and y to negatives, and the equation is unchanged. And according to the criterion here, the graph has a symmetry with respect to the origin, as you can see in here. It's just like the graph has two branches. One on the first quadrant and the other in the third quadrant, but there are like reflections of each other across the origin, isn't it? Any questions? No? So let me just move to the next example. No, not all the graphs have symmetries. Obviously, uh, there are a bunch of tons of functions that will not meet any of those three types of symmetries we just discussed. For example, the equation y equals x cubed plus 1, if you change x to negative x, the equation just becomes y equal to negative x cubed plus 1, and the cube of negative, you get negative. So the equation is just y equal to negative x cubed plus 1, and that's different from the equation we have in the problem. So, so we do not have a symmetry with respect to the y-axis. Okay, remember, I change x to negative x to test the symmetry of the graph with respect to the y-axis. All right. And similarly, we can change to negative 1 and see what happens to the equation itself. And this time we got negative y equal to x cubed plus 1. Or if you multiply negative 1 on both sides, you get y equal to negative x cubed minus 1. So again, this is not the same equation in the original problem. So according to the criterion we have, the graph does not have a symmetry with respect to the x-axis. You know, if you want to test symmetry with respect to the x-axis, you change y to negative y and see if the equation is changed or not. So it is changed, so there's no symmetry with respect to the x-axis. Okay, so then let's just test the last type of symmetry, symmetry with respect to the origin. So this time you change both x to negative x and y to negative y in the original equation, so we get the negative y equals negative x cubed plus 1. Well, again, negative x cubed, you get the negative in here. So negative y equal to negative x cubed plus 1. If you multiply negative 1 on both sides of the equation, negative becomes positive and positive becomes negative. So you're going to get y equal to x cubed minus 1. Okay? And still, that's not same as the original equation in the problem. So, according to the criterion, this graph does not have a symmetry with respect to the origin. Remember, when you change x to negative x and y to negative y, and you see whether the equation is unchanged or not to test the symmetry with respect to the origin. And it is indeed changed. So there is no symmetry with respect to the origin for the graph. So the graph does not have any of those three types of symmetries in this problem. All right. So you can see the graph. Any questions? Okay. Okay, a related topic of symmetry of graphs is called even and odd functions. You probably learned it before. Well, these are just another way to talk about symmetry of graphs. So we talk about the functions, even or odd. So not just the equations, the relations. If the graph of a function has this symmetry with respect to the y-axis, then we call this function is even. If the graph of function has a symmetry with respect to the origin, we call it the odd function. Okay. So in other words, if f of negative x equal to f of x, then the function is called an even function, and its graph is symmetrical with respect to the y-axis. And remember, you change x to negative x, and you get the same kind of equation. And here, same function. to test the symmetry with respect to the y-axis. So, for example, the function f of x equal to absolute value of x is even because when you plug in negative x for x in this function, you can get absolute value of negative x, which is the same as absolute value of x, and that's just the fx itself. So the function is unchanged when you plug in negative x for x in the function. So the graph has a symmetry with respect to the y-axis and is even. Okay, as you can see from the graph. Any questions? Next. Odd function. Okay, obviously. This time, you change negative to a negative x to x again, and if you get another negative sign for the whole function, then the function is called odd, and the graph is symmetric with respect to the origin. So you can see if you change x to negative x, y also change to negative y, right? Okay, so that's the symmetry we discussed, the point symmetry with respect to the origin. Change both the x and the y. Okay, so for example, the function f(x) equals x cubed is odd because if negative x equals there's another negative sign in the front misstating here, I'm sorry, is equal to negative of negative x cubed, and mm, okay, no, I didn't miss anything. Okay, f(x) equals x cubed, so if negative x equals negative x to the cube, which is negative, when you cube a negative number. So that's negative of x cubed, and that's just negative of fx. So the function is odd, and the graph is symmetric with respect to the origin.